we do have 4 objectives. I can probably live with not getting to the last one, but I don't know that we can live with not getting the first 3 done. So we do want to define a new variable called electric potential difference. We want to calculate potential difference from the work needed to move a charge around. We want to describe how charges are distributed on solid and hollow conductors, and then we do want to explain the function of a lightning rod. Before we do any of that, we need to review some stuff from January, maybe? Potential energy, I think that was a little bit before we had the midterm at the end of January. So the type of potential energy that we've at least quantified so far was our gravitational potential energy. And gravity is a great analog to electricity because they're both field forces, right? They both exert forces by utilizing this concept of a field. And I think we're already fairly comfortable with gravity. So what is this thing? That. A rock? Fine. Alright, so we have a rock. And what's down here? Well, what's this? That's the same rock. And what's this, like, down here? It's like the ground, right. So we have a rock all the way up here, and this says high potential energy. I think that makes sense, because when we lift something, we're storing energy in it by placing it at a position within the Earth's gravitational field. If I lift this thing up, I increase its gravitational potential energy. And then if we let go, it falls, right? And it has less gravitational potential energy once it's fallen. In fact, if it's on the ground, we would probably say that it has no gravitational potential energy. Now, so the rock is going to do that all on its own. Well, that's not true. The Earth and rock together are going to accomplish that, right? So the rock has a natural tendency to decrease its potential energy. If we want to lift the rock back up, then we need to do work to the rock, right? The Earth and rock are not going to do that all by themselves. We have to do some external work to lift the rock back up, all right? So what's important there is that the rock has a higher potential energy up here, a lower potential energy down here. Nature will do that all on its own. Nature will make the rock go from a higher potential energy to a lower potential energy. If we want the rock to go from the lower to the higher potential energy, then we need to do positive work to the thing. Questions from anybody about that little bit of review from January? Great. So we can say all of these same things about charges, right? So just before we move on to charges, an official summary. If we do positive work to an object, its potential energy will increase. Gravitational, electric, it could be either one. But if we do work, like lifting something, its potential energy increases. If nature is doing the work, then the potential energy will decrease. Right? If the clock falls off the wall, the Earth is doing work to the clock, and it will bring it to the floor, it'll give it less, it'll take the potential energy from it. Bless you. So electric potential energy is the exact same concept as gravitational potential energy. We're storing energy in a charge by placing it in an electric field. Okay? And if we want to change the electric potential energy, somebody's got to do work. We have to do work, the field has to do work, somebody has to do work. Alright? So we have a positive charge that's creating an electric field. And I shouldn't have drawn that, I've drawn right over the locations we care about. And we have a positive test charge. Okay? The positive test charge is right here. If we allow nature to do work, will this test charge end up at position B? If we allow nature to do the work? No way, right? No way, Jose. Because this positive region of space is repelling this positive test charge, so nature is going to make it go that way. Nature is going to make it go in the direction of the electric field. So no, nature would not bring it to location B. If we want it to go to location B, we would have to move it there. We would have to do work and move it there. So, Location B would be the location of higher potential energy. And location A out of these two positions would be the position of lower potential energy, right? I would have to do work to move it to the higher potential energy position. Nature, if we're at B, nature would do the work to move it to the lower potential energy location. All right, that's really all that I want to say about, at least on this slide, about high and low potential energy. Follow-up questions from anybody about position, about the positive test charge having less electric potential energy in A and more electric potential energy in B. Great, so let's see if you have that, because on the next slide we have a different scenario. If you can, try not to read what's at the bottom. I could probably fix that, and if not, ooh, perfect. Perfect. Almost perfect. That was a centimeter shorter. So we have a negative region of space creating an electric field, and we again have a positive test charge. So take 10 seconds and think to yourself, what is nature going to do to that test charge? Right? If we let go, if it's just sitting there and we let go, what is nature going to do to that positive test charge? Which way will it be used? Okay, that was 10 seconds. So in your foursomes, can you just see if everybody has the same idea, or if not, talk about why you think differently? Okay, it looks like we didn't have to have a whole lot of argument. So nature would make it move to the left, yeah? Because the positive test charge is attracted to the negatively charged region of space. Right, the electric field points in, and the positive charge is going to, the force on it is consistent with the direction of the field. So yeah, nature's going to make it go this way. All right, so here's, I think, a harder question, just because this is a new concept. I would like, in your foursomes, for you to identify which of these positions is the higher potential energy position and which is the lower potential energy position, right? In your foursomes, whoever's most confident can talk first. Nobody's talking. Okay, so hopefully you determined that this time A is the higher potential energy position and B is the lower potential energy position. Because nature is always going to bring us from a higher potential energy state to a lower potential energy state, just like nature always causes my pen to fall towards the ground. My pen has less potential energy on the ground. Alright? So this time A is the higher potential energy position, B is the lower potential energy position. We would have to do work to move the test charge further away from the source of the field. That is all really that there is to know about electric potential energy and doing work, right? So I'm going to keep going. If you're not 100% of the way there yet, I would encourage you to think about it a little bit more. If you didn't read the textbook already, do that. You can read the captions on the bottom. Maybe that will help. It'll be in different language than I've used. So we have a very related variable to electric potential energy called electric potential. And electric potential is a little bit more important for us than potential energy. And electric potential is defined as the amount of energy per charge. So we're factoring out how much charge there is. It's the amount of potential energy divided by the amount of charge that we're stored, that's at that energy state. Just put that last electric field back up here. so we have this negative region of space that's creating an inward electric field. I think in the last diagram we had a positive charge that we had placed in that field. If we had a stronger electric field, so one way we could have a stronger electric field is by just having more negative charge. Maybe we have like 5 times the amount of charge that we had before. That means the electric field should be 5 times stronger, and our charge would have more energy, right? So a stronger field will give us more potential energy and a larger electric potential. But again, electric potential, which has a symbol of capital V, is the energy per charge. So this is measured in volts, right? I asked you when you walked in, like something about volts. I don't remember what anymore. But this is where our unit of volt comes into play. What is the energy measured in? Joules. Joules would be the standard unit we would measure energy in. And what's charge measured in? That one we know, right? Just on our quiz, coulombs, right? So a volt is the same thing as a joule per coulomb, right? So a volt is how many joules of energy are we storing divided by how much charge is storing that energy. All right, I'm going to keep going. So I said that we care more about electric potential than we care about electric potential energy. There's something we care more about still, and this is like our last new variable for today and our last new variable for a little while, and that's the electric potential difference between 2 locations. Okay, so electric potential difference, so delta V, delta is our symbol for like change in or difference, is literally the difference in potential between 2 locations, maybe location 2 and location 1, right? So maybe this is location 1 and this is location 2, I don't know. But the electric potential difference would be, what is that change in electric potential as we move from one spot to another? So that would obviously be measured in volts as well. I want to skip ahead slightly with the notes to try and have you appreciate this concept a little better. I have a bunch of different batteries up here. All right, I've got a D battery, a C battery, a AA, a AAA, a watch battery, one of these rectangle ones, and one of these huge lantern batteries. My first question, and I'll let you talk about this in your foursomes, is what is the difference between these two? In what way is this D battery different from this AA battery? Obviously the size is different, but I don't care about that. Okay, so you're not allowed to just say the size. So in your foursomes, see what you can come up with. What's the difference between these two? Come on. That for, what do you think you're going to go? They're bigger than slugs. I don't know. What are we doing? What are we doing? All right, so everybody I think has settled on an answer, and I heard 2 different answers. One was that the larger battery, the D battery, has more volts. And then the other one is that the bigger one has more energy. Same volts. There's just the one group that said difference in energy. Yeah, so the same volts. No, all right. So nobody thinks that these have the same volts, whatever the heck that means. Well, the batteries always tell you. I hate using this word. It's a bad word. We can talk about it in a few minutes. I hate using the word voltage, but I will for right now. They always tell you the voltage. So what's that one? So 1.5, and under my thumb, what's that one? 1.5. 1.5. And this one is 1.5 volts, and this one is 1.5 volts, and this one is 1.5 volts. Now, the 1.5 volts is an electric potential difference. Right? It is the difference in energy per charge between two locations. What are the two locations? Alex? Oh, you're throwing chemistry terms at me to try and confuse me. How about we go with the two terminals of the battery, right? Batteries almost always have a positive and a negative terminal identified. See, Alex is right. One of those is called the cathode because one of them is not called the cathode. One of them is called the cathode. One of them is called the anode. But what's important for us, at least today, is there is a difference in energy per charge of 1.5 volts, 1.5 joules per coulomb between those two locations of the battery. All right? So all 5 of these actually have the exact same difference in energy per charge between their two terminals. But what's different about them is this one has way more charges in it than this one does. Right? So as we let the charges go from the positive terminal to the negative terminal, they will experience the same change in energy or change in energy per charge, but there's just way more charges, right? So, I don't know, I think my remote control uses AAAs, is that right? No?
They're all different.
They're all different? Alright, well, some use AAAs, most use AAAs, maybe some use AA's. If I rigged it so that I was operating my remote control off of this, it would be difficult because it's not going to fit in the compartment. I need to use wires and such. But it would never have to replace the batteries in that thing. It would last forever. Now these actually are different. What's this one? The name of the battery. Not really. You don't know what this kind of battery is called. What is it? It's a 9-volt. That's what you call it. When you get that's the name. It's called a 9-volt battery. This is the kind you lick, right? And you can feel the charge going through your tongue. Don't do it because I just did it. So that's a 9-volt, and then this is actually a 6-volt. So there is a larger difference in energy per charge across the terminals of these two batteries and across the terminals of the other batteries. All right. So again, the electric potential difference is kind of our important variable for the rest of the year, which is measuring the difference in energy per charge between two locations. Alright, so moving on, one of our objectives asked us to be calculating the electric potential difference based on the amount of work that we do. So I just wanted to restate our electric potential difference, kind of merging it with our definition of electric potential. So electric potential difference, sure enough, is the difference in potential between two locations. I think earlier I said 2 and 1, location 1, location 2. Here I'm saying final, initial, whatever, same thing. Potential is the same thing as energy per charge, we said. So it would be absolutely correct to say that electric potential difference is equivalent to the change in energy that charges experience divided by how much charge is experiencing that change, right? So all I've done is just put in the E over Q for both of these, and I come up with this. And we also know from earlier in the course that a change in energy is the same thing as work. So for those of you that are taking IB Physics next year, where we actually need to care about definitions, very precise definitions of things, our definition for electric potential difference is the work done per unit charge in bringing a test charge from one place to another. Right? But all 3 of these are equivalent. All right, so let's use that once, but let's get this bad word out of the way. All right, voltage is not a science word. It is slang for electric potential difference, and you cannot use that word. Okay? Well, write that on a quiz, Burton, and see how fast I mark it wrong. So don't use that bad word, right? If we mean electric potential difference, say electric potential difference. If you mean electric potential, say electric potential. If you mean electric potential energy, say electric potential energy. Don't say voltage. Alright, so now that I got that little rant out of the way, let's do one quick calculation with electric potential difference and work and charge, and then we'll we'll go fast through a couple of stories and then get to distributing some charges in a conductor. So in your foursomes, see if you can solve this. How much work is required if we're going to move 1 full coulomb of charge across a potential difference of 25 volts? Okay. So maybe we have a 25 volt battery. We want to move 1 coulomb. We want to recharge the battery and move 1 coulomb of charge from the negative to the positive terminal. How much work do we have to do? So in your foursomes, yeah, I don't know, they don't do all 6 steps for this. I actually want to go pretty quick. See if you can do that. Hi. Well, the energy would, but it's based on a change in energy, so the distance is kind of already built into that change in energy. Alright, what's the answer?
25.
Yeah, you do this in your head, right? So the potential difference is the work per unit charge. We have to rearrange this because we want to solve for work. The work would be the amount of charge that we're moving multiplied by the potential difference that we're moving it across. So 1 coulomb multiplied by 25 volts. So yeah, we need 25 joules of work in order to do that. Alright, fantastic. A little bit more on electric potential difference, and then I definitely need to reserve 5 minutes to talk about charge distribution. So start yelling at me if we get, well, that gives me 2. Alright, never mind. Electrical outlet, the things you're supposed to jam forks into, right?
Yeah.
You don't jam fork, you don't jam anything into an electrical outlet. What's the potential difference across those 2 terminals?
How do none of you know that?
0. Oh, wait, 10 billion. 1,000.
It's like 120 volts. Okay? With 120 volts, a difference in energy per charge of 120 volts. What's that? It's different outside of the US. I think it's 95 or 85. I don't actually know. I haven't been outside the US in a very long time. There might be a few outlets in your house that are doubles and are actually 240 volt outlets, and they look different. They're like circular, and the little prongs are kind of arranged in a triangle. Your refrigerator is probably plugged into one of those, but you never, it's behind the refrigerator, you never see it. But 120 volts is a standard outlet. We already said the batteries are on the order of 1 to 9 volts. The Wimshurst machine, we're probably talking tens of thousands of volts in order to get the lightning that we got the other day. So it must be that the electric potential difference isn't what determines whether you get killed or not, right? Because Henry didn't get killed, and who else? I don't know who else did it. Who else did it? There's like 4 of them. Alec. There's like Thea. Wasn't Kara? Was it? Kara. All right. So they didn't get killed, but if they jammed a fork into the outlet, they probably would. So the energy per charge isn't actually the thing that's going to determine whether you die or not. All right. Real quick. You know, sometimes there's like electric lines outside that are like super high up, right? Sometimes they run like 2 or 3 down, and if you look at the base of like the scaffolding that supports those, you're definitely going to see that bad word. You're definitely going to see signs that say high voltage. Sometimes there's like orange balls attached to those. You guys sort of know what I'm talking about? All right. So those actually are called high voltage lines, and I will use the word there because that's the name of them. So high voltage lines, and this is how we kind of send electricity over fairly large distances. Like this is not on the telephone poles outside your house. This is when like the power company's sending power to like substations in your neighborhood maybe. And the potential difference across the lines as a whole might be like 50,000 volts. And the cool thing about these high voltage lines is they have no insulation on them. They're actually bare metal. Right? There's no insulator. So what happens when a bird lands on it? You know, you would think that they do, but they don't. In fact, I see birds sitting up there all the time. They actually seem to like it, and they're fine. They're fine. Why are they fine? They're not attached to anything?
We're not
Fine.
grounded.
Their feet, I don't know, they could sit on it with their butts, they'd still be fine. They're not
Isn't it alternate?
So here's the thing. What matters isn't so much. I may have actually misspoken 90 seconds ago. No, I didn't miss. The charges in this line are extremely energetic, right? They do have lots of energy per charge. However, those charges have little interest in moving through something unless there's going to be a difference, unless they can get to a lower energy state, unless there's going to be a drop in energy per charge. There is not a difference in energy per charge in these two spots where the bird is perched. So the charges cannot get to a lower energy state by going through the bird, than they would by just continuing to come to the substations in our neighborhoods. The only way that charges are going to move through the bird is if they would have a drop in energy. No, so the bird is fine. The bird is fine right now. Shoot, I'm going to 2 minutes. Squirrel. Hate squirrels. Hate them. Stupid squirrel tails, right? They can climb up these things. And what happens when they get up here? Let's have a stupid friend over here. So the stupid squirrel friend with the stupid squirrel tail is just about ready to grab onto this line. What's going to happen as soon as he does?
It's eased.
This is metal scaffolding. Right? We don't want to use wood. Wood isn't strong enough to hold this stuff up. We have metal scaffolding. And these lines are connected to the scaffolding with insulating stuff. But as soon as the squirrel holds on, the charges that are in the scaffolding probably have no potential. Connected to the earth, they probably have no potential. The charges up here are at 50,000 joules per coulomb of charge. As soon as the squirrel touches, I don't know why he has 3 feet, but he does. There will be a potential difference of 50,000 volts across that squirrel, and you better believe that charges are going to move into the scaffolding to get to that lower energy state, and he's going to be charcoal. Right? He's going to be dead. He's going to be crispy dead on the ground.
Wait, let's make this different.
But we're okay so long as there's no potential difference. There's a potential difference of 0 across the bird's feet. Bird's fine. Henry, if the squirrel jumped from the scaffolding onto the line, he would be okay if he did a big jump. If he did a little jump, then we probably could charge by lightning through small amounts of air. I think I have 20 seconds. So what we didn't get to is, we didn't get to our last 2 objectives. That's all right, because I can do those in like 5 minutes next class. So we still need to describe how charges are distributed on solid and hollow conductors, and we still need to talk about a lightning rod. I'm probably going to have to go 10 minutes maximum. I'm hoping for 5.